Okay, well, I think today's lecture is kind of long, so we will just dive right in and hopefully get things done. So announcements, let's see. There's a homework, it's due Monday. The project two design doc draft grades are on Gradescope, so take a look at those. The entire project is due next Tuesday, and there's a lab. Okay, so last time we talked about TLS. TLS is the protocol for securely communicating across the internet. So as we built from lower layers to higher layers, the one thing we were almost always missing was cryptography, or using some sort of cryptography to secure our communication. So TLS was the protocol that would solve all this for us. And to start a TLS connection, you run this kind of long handshake, and it had a lot of different steps, and we talked about what they're for. So in the two hellos, there are nonces, and the random nonces make sure that every handshake looks different. So any two handshakes will never have identical outputs or identical symmetric keys derived because there are nonces here. And then the server sends the certificate to prove that it owns the public key. And you use either an RSA key, an RSA exchange, so encrypt the pre-master secret and send it to the server, or use Diffie-Hellman, where you perform a Diffie-Hellman exchange with the signature from the server. And this lets the client and server agree on a secret key, because you're using public key cryptography to make these two people share a key. And you're also additionally proving that the server owns the private key. This makes you confident that you're talking to the correct server, because the certificate tells you their public key, and they've solved some sort of challenge to prove that they own the private key. And then after you're done with that, you exchange some MACs to make sure that no one has tampered with the handshake yet. So you derive symmetric keys using the nonces and the pre-master secret, and then you exchange MACs across everything sent so far to make sure nobody tampered with the nonces or the certificate or anything like that. And then once you're done with that, you can use symmetric encryption and MACs to send messages so that you have confidentiality, integrity, and authenticity. And finally, someone could try to replay a message within a connection. So they see a message, record it, and then resend it over and over. And to prevent that, we use record numbers inside of the encrypted packet. So they're not quite sequence numbers because they're encrypted and they're used for security, but the idea is kind of the same. So different messages have different record numbers. And then we talked a bunch about the security properties. So Diffie-Hellman has forward secrecy, which means if someone steals our keys later, they can't decrypt past recorded communications, but RSA does not have this property. And then we talked about how TLS always has end-to-end security, which is great. That means that even if everybody in between you and the server is malicious, your TLS connection can still be secure, because nobody in between you, whether they're man in the middle or on path or off path, can tamper with your connection without being detected. But there are some drawbacks. So TLS is not anonymous. People can figure out who you're talking to. And doesn't provide availability, because connections can get dropped or censored. So it's not perfect, but it's pretty good. And then we talked about how TLS is used by application layer protocols like HTTPS to secure web communication. So that connected us all the way to the very top layer. And then at the end, we talked about a bunch of blue slide optional content. And it basically could be summed up by saying it's hard to find a way to trust certificate authorities. So we have to have some sort of root of trust, and it turns out that having a root of trust can be hard. So that was last time. And notice that because of last time, we're basically done with the entire network stack. So we started at the bottom, and then we worked our way all the way to the very top with HTTP and web. So if we're done with all of the web or the network stack, then what is today all about? Well, it turns out there are a couple of kind of side questions that we have to solve. So before we can get a perfectly working internet, we still have a couple of things left to clean up. And that's what today is all about. So today's DNS, and it's going to be one of those side problems to solve. So if you remember from the web unit or just your own browsing of the web, you might remember, well, I guess first of all, that computers are addressed by IP addresses on the internet. So we've talked about this a lot in the networking unit already. Every computer has an IP address that's unique. And if you want to talk to another computer, you use their IP address to send packets to them. So we talked about that a lot before. Here's an IP address. It's just some numbers. Now, machines like numbers because numbers are easy to process for machines. And because if you remember from the BGP lecture, these numbers actually contain some information about where this machine is. So maybe the computer looks at these numbers and realizes, oh, I should probably send the packet this way or this way just by looking at the numbers. So machines like this, but humans don't like this because do you really want to remember 4 different numbers for every single website you visit? Right? Like if you want to make a Google search, you have to remember 74, 125, 25, 99. That doesn't sound very appealing. So if you remember from the web unit, what we used for as humans are human readable domain names. So here's a domain name, it's google.com. Now this is great for humans because we can read words and we can remember words very well. So this is good for us. But it's not good for machines because a machine who sees www.google.com has no idea where this machine is. They like IP addresses because that tells them where to send the packet. They don't like domain names because domain names are just words to them. They have no idea where this is. But again, it's good for humans because we can remember these and use them in our life without having to remember a ton of numbers. So this is kind of a problem, right? We as humans are using one addressing system, which is domain names, but computers are using a totally different one, which is IP addresses. So how do we connect these two? And it turns out today's entire lecture is just about how to connect these two. I guess one thing to note is that domain names are not URLs. So remember from the web unit that a domain name tells us exactly which server to contact. So the URL had all these different parts, and the domain part just said, there are all these web servers on the web. Let's pick one to contact. So that's just the domain part of the URL, right? Like this is not part of a domain because it's the path, and that tells us like what file on the server I want to access. But that's not the same as the domain. The domain is all we care about today. So all we care about today is finding a machine on the internet to talk to. Okay, so just to keep in mind. Okay, so what's the point of DNS? As you might guess, all we're doing today is translating human readable domain names to machine readable IP addresses. So today's entire lecture is just figuring out what kind of protocol are we going to use to translate from www.google.com to this pile of numbers on the right. So kind of the way it works is, let's say you're browsing the internet or browsing the web, and you want to send a packet to a certain domain. So for example, you open your browser and type www.google.com. Now your browser, your computer needs to send some packets to google.com to retrieve the homepage or make a search or something. So you need to make a request to google.com, but google.com is the human readable name, and we have no idea where it is yet. So this is where DNS comes in handy. You are going to perform a DNS lookup. So you're going to go and look up the IP address of www.google.com. And then somehow with some protocol that we'll see, you'll eventually get this answer and learn that this is the IP address of google.com. And once you learn that, now you can make the packet requests to this IP address. So that's the goal for today. And then now we can actually see how it works. So when we make a lookup, that means we're asking someone this question, right? We have to ask someone the question, what is the IP address of this? So can you translate this for me? So if we have this question to ask, someone has to be answering it, right? Someone's job has to be telling us what this answer is. And it turns out there are actually servers on the internet whose entire job is just to sit there 24 hours a day answering DNS requests. So these servers are called name servers. And again, basically all they do is just sit there and they receive a bunch of DNS requests and then they answer them for you. Name servers also have domain names and IP addresses. And this is kind of hard to sometimes wrap your head around. But if you think about it, this name server is just like any other server on the internet or the web. It's providing a service to everyone else. And you can talk to the computer because it's a computer on the internet. So just like any other computer, it also has its own domain name and its own IP address. But its sole purpose in life is to answer DNS requests and tell you what other domain names have corresponding IP addresses. So you still have to have a way to talk to this server. So it does have its own domain name and its own IP address. But when you talk to the server, you're not going to get a web page or HTML or JavaScript or anything. All you're going to get is the answer to your DNS queries. So here's an example of a name server. This one says a.eduservers.net. That's the domain name, as we've seen before. And here's an IP address. And it turns out if you actually contact the server in real life, you will be talking to a name server. I think if you type this in your browser, you'll just get an error because, again, name servers are not serving HTTP. So they're not here to serve you HTML websites. They're just here to answer your questions. So I think either you get a generic message that says you have visited a name server, or you just get an error. But yeah. So if we think about the usage from before, it's basically the same. We're going to perform a lookup, but to perform the lookup, we're actually going to send a request or a query to the name server. So we are going to create a packet with a question inside, and the question will say, what is the IP address of google.com? And we'll send this question to the name server. And the name server will give us a response because their job is to answer our questions. And they'll answer the question by saying, the IP address of google.com is this. So to learn their IP address, we actually have to make a request to a different server. Okay, there are some issues with this. So this would be a great design and we could be done right here, right now, but it's not perfect. So there are some issues, and that's what the rest of the lecture is all about. One issue is the internet is really, really, really big. There are a lot of domains and there are a lot of IP addresses, and there are a lot of people using the internet and requesting IP addresses at any given time. So it's not like we can just have one gigantic name server that answers every DNS request in the entire world. That would be really great if it worked, but there just isn't any computer that's large enough or has enough bandwidth to possibly do this. So we have to be a little bit more clever in our design. And you could say, well, okay, instead of having one gigantic name server that answers every single DNS request from everyone, because that's just not feasible, how about we have lots of different smaller name servers, and each name server answers some requests, but not all requests? Well, that's a better idea, and it's kind of similar to what we're going to see that the actual solution has been. So we'll split one gigantic name server's job into several smaller name servers, and they'll all kind of do their own job. But there's still kind of a problem, which is if there are so many different name servers and each one is handling a different job, how do you know which is the right name server to talk to? We haven't solved that yet either. So these are the two problems we're going to solve, I guess, now. Okay, so if there are lots of name servers, then we're going to arrange them into a hierarchy. Someone asked, how do browsers know the IP of name servers? Is it built in? Yeah, so that's a really good question, and it's basically one of the questions we have to answer, which is, if there are multiple name servers, how does the browser know where they are? Like, how do we know where to contact them? Where do we send this question back in at all? So that's a very good question, and basically a lot of DNS design is solving that one question. So before we solve it, we have to first think about, if we have all these different name servers, it would kind of be awful if each one just served a random subset of domain to IP translations, right? It would really be bad if this name server said, well, I choose today, I'm going to serve google.com's IP address, and I'll tell people that answer, but I don't know the answer to, I don't know, berkeley.edu, or I don't know the answer to mit.edu. That would be really hard to manage because you have all these different name servers and it's not clear who can answer what. So not only do we have to present a bunch of name servers, but we also have to figure out who is responsible for what. So to do so, we basically arrange domains in trees. So here's a tree of name servers, and all of these are going to be name servers, and we'll see how or why they're arranged in a tree, I guess, in a second. So there are two big ideas for how to make this multiple name server structure work, right? As someone said, we have to figure out how to contact them, like where they are, and if they don't know the answer, what do we do? So there are a couple solutions here. The first solution is, if a name server doesn't know the answer to your query, they have another job, which is, if they don't know, they have to tell you someone else who can get you closer. So it's not okay to just say, I don't know, sorry, tough luck. If you don't know, your job is always going to be to find somebody else who knows better. So it's not okay to just say, I don't know, and give up. You need to give this person, or the person who asked you the question, a better answer. So maybe you don't know, but you'll say, well, this person might know, so go talk to them. So kind of the analogy here is like, well, if I don't know the answer to your question, I will redirect you to a friend who can help. So that's kind of analogy here. And then the second idea, which we've seen here, is instead of just arranging the name servers randomly, because then you might be bouncing around, right? You might say, I don't know, go as Bob. And then Bob will say, I don't know, go as Alice. And then Alice will say, I don't know, go as Bob. And you'll be bouncing back and forth and you'll never find an answer. So instead of having just name servers all over the place, we're going to organize them a little bit. And we're going to organize them into a tree. And the reason why a tree is great is because you can always work your way down the tree and you're always going to hit the bottom eventually. So you'll always receive the answer. So maybe you ask this top name server and they say, I don't know, but I'll take you here because this person might know. And you ask this person and they say, well, I don't know, but I'll get you closer. I'll tell you this person might know. So you ask this person and they give you the answer. So by arranging the name servers in a tree, you're basically guaranteeing that after a certain number of redirects, so after kind of bouncing around and saying, you should go talk to this person, and they say, you should go talk to that person. And eventually, after enough steps, you'll always receive a DNS answer because things are in a tree, so there's no like cycles or anything. And you're always working from the top of the tree down. So that's the kind of big idea of how DNS works. I will pause briefly if anyone wants to ask anything else. Okay, onwards. I don't know why this branch suddenly went missing, but pretend it's there. So as we said before, every box here is a name server. And the way we're going to divide up the work is by domain. So as you might guess from the names of these name servers, the label inside here tells us what the name server is responsible for. So because we can't have one name server responsible for everything, we are going to have these name servers responsible for kind of subdomains or zones of the internet. So for example, this name server here, it will answer everything that ends in .edu. So if you ask it for east.berkeley.edu, it's like, okay, I can tell you about that. If you ask it for mit.edu, it'll say, yeah, I can tell you about that. Or stanford.edu, I can tell you about that. But if you ask this edu server for google.com, it'll say, I don't know, that's not my job. Right? So every name server is responsible for a zone of the internet. And the zones can get more specific as you move down the tree. Okay. I think that's it for the name server hierarchy. We'll see this in a lot more detail, so don't worry if it doesn't totally make sense yet. Okay, but at this point, I think we're ready to see our very first DNS lookup. So we're going to try and look up a DNS query. So we're going to try to ask the DNS name servers what the IP address of eeks.berkeley.edu is. So maybe my browser wants to visit this website, but before I can visit this website, I need to figure out what the IP address is so I can send packets to this location. Okay, every DNS query starts with root. So you always start at the top of the tree and move your way down. So no matter what, every DNS request will always start way up here. And you will always ask this person the exact same question, which is, what is the IP address of eeks.berkeley.edu? Because that's your question. So we'll ask root the question. And why is it okay that we're asking the root the question? Because the root is the top of the tree. So the root can answer anything and is responsible for answering anything. Now, they might not give you the answer right away. They might have to tell you to go somewhere else for the answer, but they are responsible for basically every domain. So they're on the hook for everything. So eeks.berkeley.edu is a domain and the root is responsible for all domains. So it can't hurt to ask them. Maybe they won't have the answer for me, but at least they'll get me closer. So that's our goal. So the first thing we'll always do is ask the root, do you know the IP address of berkeley.edu? And the roots will say, I don't know, but I can get you closer. So even though I, the root, don't know the answer, I'll get you closer. So I'll tell you, you should talk to this .edu name server, right? So because the domain we're asking for is eeks.berkeley.edu, it makes sense that we're going down the edu branch and not the .org branch or the .com branch. So the root will say, I don't know, but let me take you down this branch and let me have you met my friend, the .edu name server, and it'll say, you should go talk to this .edu name server, and I'll tell you, they might know the answer, but even if they don't know the answer, they can get you closer. So go talk to them, and I promise you, you're going to get closer. So you didn't get the answer, but at least you got closer. So let's keep going. Now let's ask the .edu name server because root told us to ask this person. So let's go ask this person and say, what's the IP address of eeks.berkeley.edu? So we asked the exact same question because that's what we want to know. And the edu server is unfortunately going to say, I don't know either, sorry. But again, I can get you closer. So as promised, I am going to get you closer to the answer. And again, there are a bunch of different branches here, but the right branch to go down is the berkeley.edu branch. So I will tell you to go visit the berkeley.edu name server. And I promise you, either they'll know the answer for you or they'll get you closer. So again, I don't have the answer, but I got closer, so that's good. And finally, I'll ask down here, I'll say, well, the last person pointed me to you, so do you know the answer? So what's the IP address of berkeley.edu? And again, they'll say, oh, wait a minute, they actually know the answer. So they'll give me the answer, the IP address is this. And because we have the answer now, we're done. So it took a bit of traveling down the tree back and forth, but eventually we got the answer. Okay, any questions? Good so far? And again, we'll see this quite a few times in detail, so don't worry, it'll come up again and again. I guess I never made pictures or anything for an analogy, but the kind of funny analogy that comes up is sometimes if you're walking around in the city or something and you really have to use the bathroom, but the only building nearby, like this really big office building, and you have to ask people where the bathroom is. So you might ask the front office, like, do you know where the bathroom is? And they're like, I don't know, go ask this person. And I'll ask them, do you know where the bathroom is? They'll say, I don't know, go ask this person. And then eventually you bounce back and forth, but eventually you find the bathroom. So life is okay. Okay. So that's the DNS query. There's kind of one extra bonus step here that we have to talk about, and that's the stub resolver and the recursive resolver. So in practice, it's kind of annoying if your computer has to do this every single time, because you have just made, 3 packet requests just to receive the answer. And that's a little bit annoying for your computer to have to do every single time. So a lot of internet service providers, right? Like if you're paying for your internet by paying Comcast or whatever, they'll usually give you an extra service, which is they will help you make DNS lookups. So the way this works is your computer is actually just going to ask a resolver on the local network and say, can you do this for me? Can you go find out what this DNS, why don't you go find out what the IP address of google.com is? And that's the recursive resolver. And the recursive resolver is going to do all the work for you and do all that back and forth pinging back and forth that we just saw. And once the recursive resolver finds the answer, they will come back and give you the answer. So there's kind of a benefit to this structure, which is that if everybody is using the same recursive resolver, they can actually cache a lot of answers. So if someone before you has already asked for eeks.berkeley.edu and you ask the recursive resolver, they'll say, I don't even have to make requests. I know the answer already, so here you go. So they might even save you a couple of round trips. So in pictures, the way this looks like is, this is you, you're the stub resolver. So your computer only has a stub resolver, and it will never try and go to talk to all these name servers by itself. It's going to make someone else do it. So your stub resolver will say, there you go. It'll say, hey, recursive resolver, can you go find out what the IP address of eeks.berkeley.edu is? I don't want to do it, so why don't you do it for me? And the recursive resolver will say, okay, I'll do it. And it'll go back and forth like we just saw. So it'll talk to root. Root says, I don't know, go ask.edu. It'll go to .edu. Edu says, I don't know, go ask berkeley.edu. And then the berkeley.edu name server will say, I don't know, go ask. Or actually, I do know, so here's the answer. So the recursive resolver will do all this work for you, talking to all these name servers. And I guess I just talked myself into one common mistake that people make, which is, for example, this one says berkeley.edu, but it's careful to note that, you have to be careful to note that this is not the berkeley.edu web server. So if you talk to the server, you are not receiving like the Berkeley homepage or anything like that. This is the berkeley.edu name server. So this server does not have any web functionality. It's not going to give you any HTML pretty looking Berkeley website. All it's going to do is tell you the IP address of the actual web server. So that's one thing to make note of. So even though it says berkeley.edu, and sometimes we'll just refer to it in words as, yeah, I asked berkeley.edu and I got an answer. It's important to remember this is not the web server, this is the DNS name server. And its only purpose in life is to answer your DNS requests. Okay, but anyway, the stub resolver asks the recursive resolver to do the work for them. The recursive resolver goes back and forth, as we already saw. And then once they have the answer, they just feed it back to you. So this makes your life easy if you're a computer and there's a recursive resolver somewhere on the network. All you have to do is make a single request and you get the one response back. So from your perspective as a stub resolver, life is good. All you have to do is make this request. And from the recursive resolver's perspective, well, they have to do a bit more work, but things are still more efficient because this person can cache a lot of requests. So maybe a different stub resolver on the local network has already asked for each.break.edu, in which case you make the request, the recursive resolver looks in their cache, sees the answer, and just feeds it right back to you. And we didn't even have to do steps 2, 3, 4, 5, 6, 7. So that's also nice. Now, as a stub resolver, you can probably also cache, but the recursive resolver will have a bigger cache because a lot of different people on the local network are all relying on this person or this machine. So they'll probably have the bigger cache, which is good. Okay. So that's the stub resolver. And I think at this point, we're pretty early in the lecture, and we're not going to take a break yet, so sorry if I cut your hopes up. But if you understand how this kind of diagram works, so if you understand how you're going back and forth, you're basically good for DNS. This is the entire protocol for how DNS works conceptually. So if you made it this far and everything still kind of sort of makes sense, then you're in very, very good shape because this is what DNS is in real life. So we haven't really simplified anything. You're looking at the real DNS already. But because we're going to try and show you some kind of real world things you can try yourself, now we're going to dive a bit more into like, how would someone code this? So if you were a programmer or a system admin or a designer of the internet, how would you actually implement this in code in a way that's very efficient and resist attacks? So this is great, but it's not quite like as low level as we want to show you. So for the next 20 minutes or so, we're going to start diving really deep into the implementation of DNS. So I guess like hold on and hang tight, but we'll get through this. So one kind of question we have to ask ourselves is, what protocols do we want to use for DNS? So remember, at the transport layer, you had two choices, right? So maybe at the IP layer, you have to use IP, but at the transport layer, you have two options for how you want to send all of these messages, right? They could be sent over UDP, which is the unreliable version, or the TCP reliable version of the transport layer. So again, UDP has no guarantees. Stuff can get dropped or reordered, but it's faster because you don't have to worry about a handshake or anything. TCP is slower, but it guarantees that packets show up in an order. So these are your two options. And I realize that the title completely spoils this, but it turns out DNS uses UDP. And the reason why is because DNS has to be really, really fast. When you're designing DNS, your number one goal, and the people who designed this, I think it was even higher priority than security, which might have been a bad idea, but their main goal, no matter what happened, they wanted this thing to just be fast. And we mean really fast. Now, why would you want a DNS request or response to be fast? Well, if you think about it, we make a lot of DNS queries every single day. Anytime you type in a website in your URL or a URL in your browser and try to visit a website, you're making a DNS request. If you click on a link, you're making a DNS request. If a web page is embedding an image, that's another DNS request to find the IP address of where that image is located. So you're using DNS a lot. And in fact, it's like once every single time you make a request, almost. Right? So short of some caches, you're basically doing this every single time. So because you're doing this so often, and because a DNS request could involve bouncing back and forth quite a few times, like in the last one, it was, 6 or 7 messages, we want DNS lookups to be super fast because we don't want to waste people's time and make the internet slow. So DNS has to be really fast. And between these two options, we're going to go with the faster one, just because we want DNS to be fast. And why is this good if you think about it a bit more? Because there's no three-way handshake. So if we had used TCP, every single DNS request would have to also do a three-way handshake. So every single one of your web requests now has an extra three-way handshake in front of it, which would slow things down a little bit. So that's good. And also, if you think about it, the DNS request and response are kind of one-to-one, right? You make a single packet with a request, and you get one response back. So there's no real need to make sure things come in order because there is no order. It's a single packet and a single packet coming back to you. And if you make the request and the response doesn't show up, what do? You just resend the request. So TCP is good, but it's not that useful here because you don't really care about things showing up in order. All you want to do is fire off a single packet and then get a single packet back. And if it doesn't show up, just fire the packet a couple more times. So we like UDP here. So what does the UDP packet look like? This is, we saw this already in the UDP lecture. A UDP packet has a header and then it has a payload. So what's in the header? The header has a source port and a destination port. And as you recall from the ports lecture, the source port, at least from the request. So if we're thinking about the request, it goes from client to server, right? So the source is the client port, and this can usually be chosen to be whatever, and it can be randomized for security, as we'll see later. But if you remember from ports, the room numbers in your own house or your own apartment, they can be whatever. Nobody cares what they are. So this can just be any random number as long as you're expecting a response on the same port. But the destination is kind of like the public building. We need a secure or a constant room number here. And the destination port is usually always port 53. So the DNS name servers are always set up so that they answer requests on port 53. Oh my God, my voice is blowing out. Okay, I think we'll get through this though. So DNS name servers always answer requests on port 53, which is like a constant port, and they're configured so that any request to port 53 will be treated as a DNS request. And most other ports are basically just not in use. So if you try and send it to a different port, you're probably just going to get an error. And it's a checksum just to make sure things aren't randomly corrupted, but it's not cryptographic. And you don't have to worry about it. And there's a length, which you also don't have to worry about. Okay. So now let's look at what's inside the DNS packet. And if you remember those kind of like multiple header structures, the DNS packet itself also has a header inside. So this is metadata not for UDP. UDP doesn't care about any of this. And to the UDP perspective, this is just data or bytes. But the DNS people do have to care about this. And the DNS protocol will actually have some headers for bookkeeping. So one important header you have here is the ID number. The ID number is important because we have to associate a response with a query. So let's say your computer fires off 10 different DNS requests at the same time, right? Like if you're Wikipedia surfing or something, you might click on a ton of links at the same time, and you're making lots of different DNS requests. So if you fire off 10 different packets and you get 10 different UDP responses back, how do you know which one is for which request, right? If I fire off 10 packets and I get 10 back, how do I know that this was the answer for this request and this was the answer for this request? So that's what the ID number here is for. Every DNS packet has a 16-bit ID number, and its importance is for associating a response with a query. So when I make a query and it says, oh, this query has ID number 20, the response will always come back with ID number 20. So I know, oh, this is the one that answers my question number 20. And if I make multiple requests, I can make requests 20 and 50 and 500 and 2000 or whatever. And the responses will always come back with the same ID, so I can match them up. And the client usually just picks this randomly. So the name server uses the same one in the response, as we said. And again, as we'll see later, these two have to be random for security. Okay. And then there are counts here. So the counts tell us how many records are in the payload. And we're going to talk about this more in detail later, so hang tight. Okay. So what do we mean by records? Well, that's what the DNS payload is like. So this payload, remember, it has to have questions, it has to have answers. If someone doesn't know the answer, they have to tell you where to go next. That's a lot of different information to keep track of. So how do we organize that if we're designing something like this? And the way that the DNS people chose to organize it was using records. So every DNS payload is separated into resource records or just records. And there can be a lot of different records here. There can just be one record, there can be no records, there can be multiple records. And the way they're going to organize this is every record is a name value pair. So it has a name and it has a value, kind of like a dictionary. And The records are sorted into 4 different sections, as you see here. There's a question section, an answer section, authority, and additional. And again, we'll talk a lot more about them. But just know that when you're sending and receiving DNS requests and responses, everything is organized into records. So this is kind of like our way of keeping track of what's being asked and what's being answered in a way that doesn't just create like blobs of data. Right? This is a very easy way for everyone to process things. And records are very good for caching, as we'll see later. Okay, so what does a record actually look like? Well, as we said, there's a name-value pair, but there's also a type associated with it. So it's actually name value plus a type. And depending on the type, the name and the value have different meanings. So for example, there's one called A, stands for answer. These are used for answers. So in an A type record, the name is a domain name and the value is an IPv4 address. That's a record, right? And the type tells us that if you look in the name column, you'll see a domain name. If you look in the value column, you'll see an IPv4 address. So that's what the type tells us. The other type is the name server type. And this type is used for, remember how we said if you don't know, you got to go ask someone else. So this name server type is for kind of referring you to a friend. So this is the I don't know, but talk to a friend type. So the A type is for when you know the answer. The NS type is for when you don't know the answer and you're trying to go find a friend. But there are a lot of other types, but these are the 2 you need to know for now. So if you look at a real DNS query, you'll see lots of different fancy types. And I think we'll talk about a couple more tomorrow. But for now, just imagine there are 2 types. And records also have metadata. This is kind of boring, so let's just ignore it. Right? There's a time to live, which tells us how long the record can be cached before being deleted. And there's a bunch of other really uninteresting metadata fields. Apparently, they were so boring, I didn't bother to actually type them out here. So that's cool. Okay. I guess there is a blue slide for us to learn about some different record types. Sometimes you see this one, record type. This one maps a record or domain name to an IPv6 address. So remember, IPv4 uses 32-bit addresses, but the internet ran out of addresses. So IPv6 has longer addresses. And if the A record is for a short address, how do I have a record type for a long address? I just called it AAAA. Very clever. There's one called CNAME, which comes up sometimes. This is for kind of redirection or aliasing. So if you ever go to a website and you get redirected, the CNAME might be doing that for you. There's MX if you want to send emails. I've never seen it before, but okay. There's SOA. I don't even care what that is. But yeah, you see these sometimes. So enjoy. But yeah, this is all blue, so we'll never ask you about these on exams or anything. Okay. Back to records. So we talked about there are 4 sections, right? So why are we sorting records into sections? That's because in addition to types, records can be used for different things. So maybe my record is to encode a question. So if I'm encoding a question, I'm going to put that in the question section. That makes sense. Now, the question section is actually going to be included in both the request and the response. The reason here is because when someone answers your question, they're going to also tell you what question they answered. So it would be kind of useless if the DNS server just came back to you with the answer, but didn't remind you, oh, by the way, this is the question I'm answering. So they'll usually include this in the response. Now, this is usually an A-type record because you are trying to find the answer. And we'll see this again in detail later, but yeah, just keep that in note or keep that in mind. The answer section is, as you might expect, used for direct answers. So if someone knows the answer, they're going to put it in the answer section. And that's a very easy way for you to look and see if you got the answer. If the answer section is blank, you got no answer, and you have to keep looking. If the answer section has a record, hooray, you have the answer, and you're done. In requests, these are empty because when you're requesting something, you don't have the answer yet. So as you might expect, they're empty at that point. And then if the name server does know the answer, they'll fill the answer section for you. And this usually is an A-type record. Why? Because A is for answer. The other 2 sections are a little bit funkier, so let's walk through them. The authority section is used for delegation of authority. What does this mean? It basically means, remember how we said if someone doesn't know, they have to tell you to ask a friend? That's what the authority section is for. So officially, the terminology that's being used here is delegation of authority. That's a very fancy term. And basically all we're saying is, I, the root server, or the edu server, whatever, I had authority to answer for the Berkeley.edu name server. And now I'm going to pass this authority and delegate it to this person who will also have the authority to answer that question for you. So basically, I'm kind of saying this person will also have the power to answer that question or to take you closer. That's a very fancy way of thinking it and a very formal way of thinking about it. I prefer thinking, I don't know, go ask Bob. And to me, that is what the authority section is. Again, these are empty in requests because when I'm asking you a question, I don't care about this. But when someone's answering and they don't know, they're going to have to say, go ask Bob. And like we said, this will help you direct the resolver to the next name server. And this is where the NS records come in play because we said NS records are used for delegating authority. Okay. And the final section is additional section. I think, what's going on here? Oh, there it is. The additional section is some additional information to help with the response. So sometimes the data from before is not enough to direct us to the next person, and we need some extra information for help. Sometimes these are called glue records. I'm actually not entirely sure why they're called that, but I guess they're the glue that holds this protocol together. So thank you, additional section. But if there's some extra information that's needed, as we'll see later, it'll usually get shoved in here. So if you need some domain location or something, it'll show up here. So it's shown in words here, but I like the diagrams better, so we'll skip there. Okay, but that's the additional section. We can quickly talk about caching. So as we said, this record structure, it can get a little bit complicated. And there's all these different categories and types, but the real power of using records is it makes caching super easy, right? Literally every piece of data in DNS, whether it's a question or an answer or an authoritative record or a, I don't know, go ask someone else record, everything's a record. So if you receive a record as a piece of data, you can just cache it. And now you have this beautiful cache that's just a pile of records, and you can always look stuff up in the record cache. That's so nice for caching, right? Instead of just having like random data lying around. So like, I'll just make a note here. Oh, by the way, this is this, and this is this, or whatever. This record structure is very organized and it makes caching super nice. So that's part of the reason why we use records. And as we said, records are cached until their time to live expires. So records usually have an expiration date and say, you can cache this record, but IP addresses sometimes change. Sometimes the records are invalidated, so don't keep it for too long. And after this time, you should ask again to get the latest information. And as we said, caching is super great because we want DNS to be fast. If a record has been cached, I don't have to go ask someone else for the answer. I already have the answer cached. So that'll save me a lot of queries. So that's great. And there's another kind of benefit here, which is we're being gentler on name servers. If there was no caching, every single request has to ask all those name servers. That creates a huge load on the name servers. If we're caching, then we don't have to ask the name server as much because we're going to often have the answer already. So that's really nice for the name servers who can do a bit less work. Okay, and the name servers not being overloaded also means responses will usually come back to you faster. So caching is good for everyone. We really like caching. Okay, at this point, I think we're finally ready to look at the entire walkthrough. So this is exactly what your computer is doing when you run DNS. So all the way down to the bottom of your computer, your operating system is actually doing this, which is kind of cool. So here's how we're going to do it. We're going to use something in the terminal called dig. I think Nicholas and I were trying to figure out if this is supported on Windows because Windows terminals are funny. But I know for a fact it's supported on Linux, and I'm almost certain it's supported on Mac. But yeah, this is the utility that basically shows you how DNS is working. So the operating system does this automatically, but if you want to play with it yourself, you can actually go and use dig. I promise you dig will not destroy your computer or anything. It's a perfectly safe, perfectly harmless utility. So if you're bored, feel free to go play with dig and I guess enjoy yourself. But if you want to play with dig and you want some interesting things, make sure to add the no recurse flag. If you don't add no recurse, the dig utility will do all the lookup for you and you will not have as much fun. So the no recurse will let us walk through every single step and have maximum fun and spend maximum time on this set of slides. So we have to tell dig what we're looking for. So hello dig, we're looking for eeks.berkeley.edu, just like before. Who are we asking for this query? Well, we have to figure out who we're asking. We're asking the root server, and someone asked this earlier, but how do we know where the root name server is, right? The root is, it's kind of hard to figure out where they are. So usually, because every request starts at the root, we're going to hard code the root name server IP into recursive resolvers. So the resolver will have a hard coded root IP address. So it doesn't have to ask for where is root. everyone knows what root is. Okay, so by default, we looked in our hard-coded cache, or in the case of this slide, I went on Google and looked up the IP address, and I found out that this is the IP address of root. So we're going to start by asking root. Okay, here comes the answer. Oh my God, that's a lot of gibberish. So let's break it down. This entire thing is the response, and you already start to see structure, right? Here are the sections, here's the records, here's the header. So things are starting to kind of fall in place based on our design. So it's kind of cool that we talked about a design and how it's implemented, and now you can actually see like the actual extreme low level design, and it makes you feel like a really smart hacker, man. So I like it. Here's the response. Let's tune into the header first. Someone asked, if you turned off the root name server, would you break DNS? You probably would. So we'll talk about this really soon, but for redundancy, there are usually multiple root name servers that can all answer the same questions. So not only for redundancy, but also for performance. So like there's a root name server in the United States, there's a root name server in Europe, there's one in Australia, there's one in Asia probably. So you can usually talk to your nearest root name server so that you're not trying to fire a packet all the way from California to Australia, which would take a lot of time. So there are usually multiple name servers. So if one of them goes down, it's not the end of the world. If all 13 root name servers go down, the internet would probably stop working. So you don't want the root name servers to go down. But that's a good question. Okay. Anyway, back to the response. So here's a header. How do I know it's a header? Because it very clearly tells you header in all caps. Cool. A lot of things here. One interesting thing is the ID number. So here's the ID number of our response. So dig generated a request with a random ID number that was 26114. That was fired off to the name server. The name server replied with the same ID number so that dig knew that this corresponded to the same request. So there's the ID number, we see it there. Here are some flags, they're not too important for today. And here are the record counts. So we see in each section, there is 1 in the question section, there's 0 records in the answer section, there's 13 records in the authority section, and there's 27 records in the additional section. So we see the counts of all the records in the header. Okay, now let's start digging into the actual records. So again, here's the payload. It's a collection of records. There's 1 per line, and it's sorted into 4 sections as we talked about. Okay, so start with question. Here's the question section. The name is ex.berkeley.edu. Remember, name value pair. So the name is this. The type is A because we're looking for an answer. And what's the value right here? Oh, it's blank. Why is the value blank? Because I don't know the answer. So that's why it's a question, because I don't know the answer. So it's an A-type record, which means that if you look in the name column, you will see a domain name. If you look in the value column, you will see an IP address, except you don't, because I don't know the answer. But that's the A record. Someone said, I get status surfail if you're trying this at home. We can debug that over the break, but that could be a Windows thing. Maybe Nicholas can look into it. But I promise you, I tried this on my own computer like a week ago and it worked. So fingers crossed. Okay. Now, where's the answer section? I see question, I see authority, I see additional. Where's the answer? It's not there, it's blank. Why is the answer blank? Because root didn't know the answer. So if we check the header, we see there are 0 records in the answer section and it's blank because again, the root name server did not know the answer. So what does root do if it doesn't know the answer? It has to refer you to someone who can help, right? Root is not allowed to just give up and say, tough luck. Root has to point you somewhere for additional guidance. That's what authority and additional are for. So here we're going to figure out where to look next. Now, the way I would think about this is the authority section tells us the domains of where to look next. So it says, you should go talk to a .edu name server. The name server you should talk to is responsible for any .edu query, including your query. So the name in the NS record says, go talk to .edu people. The value gives you a domain and says, a domain you can talk to is a.eduservers.net. But remember, domains are not enough for us to contact them. So in the additional section, we get another piece of information which says, you know that a.eduserver.net server that I told you to talk to? Because you don't know where that is, I'm going to help you out and give you their IP address. So that's why this is an A record, because it's giving us an IP address and it says, here's the domain, here's the IP address. So because of the record structure and how you can only put name values, it kind of takes two records to communicate all the information to you. But essentially what you're getting here is you're getting the domain or the zone. So you're learning that the next person you're going to ask is a .edu name server. It's not a .org name server. It's not a .com name server. It's a .edu name server. That's here. It'll also tell us the domain of the .edu name server and the IP address down here. So it takes two records. It's kind of in different sections. But the way I think about this is basically these two records combined tell me where to go next. So it takes one NS and one A, but eventually I figure out where to go next. And as we said before, there's multiple name servers for redundancy. So it's not enough just to say, or I guess it's because, maybe if there was only one edu name server and it went down, the internet would probably break. So let's have some redundancy. And it turns out there are actually 13 different edu name servers, and they're all listed here. And you can pick whichever one you like, or whichever one is closest to you. Maybe you look at these IP addresses and you say, this one looks really far, so I'm not going to talk to this one, but this one looks kind of close, so let's talk to this one. So it's up to you, but you can pick. So I think we talked about this, right? There are usually several name servers, and any of them will work. So let's just pick the first one, because why not? So again, this NS record tells us that there's a .edu name server somewhere on the internet, and its domain human readable name is a.eduservers.net. And this one tells us its IP address, so we can contact it. And here it's in blue, right? So remember this number, 192.5630. And this tells us this is the person to go to next. So after all this work, what do we get? We got root telling us, I don't know, but go ask a friend. And it took a lot of records and stuff to get that answer, but eventually we got it. And we figured out, I don't know, go ask this person. So let's go ask 192.5630. So we have to make another DNS request. So here we go. 192.5630. We just changed the person we're asking, but we're asking the exact same question we're asking, where is eeks.berkeley.edu? So here we go. Let's ask this next person. What do we get? We get another beautiful answer. The mechanics are basically the same, so I'm not going to walk through all of it. Right? Again, there's no answer. It's blank. That means they don't know. There's an authority section because they're trying to point us to another person. And there's an additional section which tells us where to go find that person. So the authority section says, go ask Bob, and then the additional section tells you where to find Bob, basically. I don't know why Bob is so popular today, but I guess Bob has the answers. So the authority section said, here's a Berkeley edu name server you can use. It has this domain, and the additional section says this domain has this IP address. So again, I have been directed to someone else who can help. This one is 128.32.136.3. Again, there are multiple Berkeley edu name servers, so let's just pick one. And let's pick this one. 128.32.136.3. Again, I made the request, and it's the same request, but I asked a different person, right? So again, the reason why I'm asking this person is because the last name server told me to ask this person. Here's the answer. It's a little bit different, so let's slow down a little bit. Basically, what we see is the answer actually has a record inside. So there's an answer this time, and that means that we're done. The answer tells us that the eeks.berkeley.edu domain has address answer 23.185.0.1, and we're done. We got the answer, so that's great. That's the answer. Let's see. And one thing to note here is the time to live. So this tells us that I can save this answer to keep using it for the next 86,400 seconds, which is, I think, 24 hours. So for the next 24 hours, if I ever make a request to eeks.berkeley.edu, I do not have to go through all that stuff that I just went through. All I have to do is look at my cache, see this answer, and then just plug it in. So this record is valid for 24 hours of caching. And I think that brings us to the end of the process of the mechanics of DNS. So should we just take a break and then come back for security? That sounds like a plan. And I think we'll get through it. So let's take, I guess, a 3-minute break until 4:38. Does anyone have objections or questions before we do that? Okay.
I was just gonna say, I guess I'm not sure why I'm getting the surf fail, but if I remove the plus no recurse, then at least I get the answer. But
oh, okay. We can, yeah, we can debug it during the break, I guess. But let me just pause the recording so people don't.
Oh, my bad. Sorry.
Don't worry about it. It's my bad. Okay. Okay, and we're back. So we've talked about all of how DNS works. And the rest of the lecture is just talking about how to break DNS. So what's the security vulnerabilities? And most of the security vulnerabilities for DNS fall under a category of attacks called cache poisoning. And what cache poisoning is you're returning a malicious record to the client. So as an attacker, you're finding some way to give the client a record that it has incorrect information. And if the client receives, I guess, the information, they're going to cache it. And that means that their cache is now poisoned. It has incorrect or malicious data inside. So that's why it's called poisoning. And the problem here is that that record will actually stay there until it expires. So you can actually force this victim to have bad data for quite a long time if you want to. As an example, maybe I want to supply a malicious answer record, and I want to say google.com has the IP address 6.6.6.6, which is the classic attacker's IP address. Right? Now, what happens now, I guess the example here is Berkeley, but if the victim visits this domain, they're going to look in the cache and they're going to figure out what's the IP address of this domain. Oh, it's 6.6.6.6. So let's send packets meant for berkeley.edu to 6.6.6.6. And now, guess what? The attacker is the man in the middle because they can forward those packets to the legitimate server, get a response, modify it however they want, and then bring it back. So they are now in between Berkeley and the victim, and they can modify or drop packets as they want. So here's an example of how cache poisoning could make you a full man-in-the-middle network attacker. Okay, so what are the kind of people who can try to do this? Like, what attackers are we worried about? Well, one attacker that we're worried about is a malicious name server. So what if one of the name servers is not playing nice and is lying to us? It gives us a bad answer, right? The malicious name server could do this, right? If I ask for this eeks.berkeley.edu and I ask the Berkeley name server, if the Berkeley name server has been hacked or decides to be malicious, this is what they could do, right? Not only can they give me bad answer here, right? Maybe they could change this to 6.6.6.6 and tell us that eeks.berkeley.edu has address 6666. But even worse, in the additional section, they can give us extra information, right? So maybe they can tell us that google.com is 6.6.6.6. So now this malicious Berkeley name server has poisoned the cache for other websites like Google. And it can do this for Google, Amazon, Facebook, you name it, whatever tech giants there are. Right? So that's dangerous. And how do we mitigate this, right? I don't want any name server on the internet. There are a lot of name servers, right? A lot of different companies and organizations run their name servers. I don't want a single malicious name server to immediately break all of my records. That would be pretty dangerous. Right? Let's see. So yeah, we made a query to berkeley.edu and we got a malicious record for Google. So that's what happened here. So we're going to be a little bit better about protecting against this. And we're going to implement something called bailiwick checking. Bailiwick is a funny word. I had never heard of it until I took this class. I think it's like a legal term kind of thing. But basically the idea here is we're going to limit the amount of damage a malicious name server can do. So yeah, maybe this name server has been hacked or is malicious, but we're going to make sure it cannot destroy our entire cache. And we're going to limit its power, basically. So it's kind of like least privilege. So this is called bailiwick checking. And basically what we're doing is the resolver is only going to accept records in the zone, in the proper zone. So we'll see what this means. Here's the definition for bailiwick, because I didn't know what it meant. It means one sphere of operations or a particular area of interest. So I guess it kind of means like where you're responsible for operating. So like, I don't know if this is a correct use of the word, but like my bailiwick is CS161. My bailiwick is not CS61A. I can't just go and change things at CS61A because that's not in my sphere of operations or my bailiwick. So you can think of it as every resolver, every name server is only going to handle records that it is responsible for. It's not going to try and give you random other answers. For example, the berkeley.edu name server, it can provide a record for eeks.berkeley.edu. If that's malicious, there's not much we can do about it because if they were being legitimate, they still have to answer this query. So no matter what, we have to let them answer this because it's their job. But we don't have to let the berkeley.edu name server answer queries for mit.edu. That's not their job. if you ask for MIT.edu, you would be going to the MIT name server, not the Berkeley name server. So there's no reason for the resolver to accept any records that Berkeley is providing for MIT. If I wanted an MIT record, I would have gotten it from MIT. So why is Berkeley giving it to me? I don't need to accept it. And this limits the amount of damage that a malicious name server can do. So now this Berkeley edu name server, they can poison any Berkeley domain, but they can't poison MIT domains or Google or any other .edu or .com domain. As an example, the .edu name server can poison MIT.edu or Berkeley.edu because these are already in its bailiwick. Even if it was legitimate, it had to answer these anyway. So there's not much you can do about that. But we don't have to let this edu name server answer google.com. I would never ask the edu name server for Google. I would be asking the .com name server. So I can reject if the edu name server is giving me a poison cache for google.com. Okay. And the root name server can poison anything because they're the root and everything is in bailiwick. So if you're running a root name server, you should probably be careful to make sure you're not hacked. Okay, so that's bailiwick. There's some to-dos that's terrible and just unfinished, but yeah. I guess what was to-do? It's like remember subdomains. Okay, so yeah, if you want to be formal about this, you can think of it as like this name server can provide anything in its subdomains. If you remember those from the web unit, if you don't, it's kind of, I guess, intuitive to just think, well, Berkeley.edu would not be providing something for google.com. So that's bailiwick checking. Sorry for the unfinished to-do. Okay, so that's the malicious name server risk and the defense. Let's now talk about network attackers. So there are a few network attackers, as you remember from a couple lectures ago. There's the man in the middle, there's the on path, there's the off path. This section is going to look very, very familiar to you because it's the exact same structure that we had in TCP with these network attackers. And I think also with ARP, maybe some of the lower level ones too. So as with those lower ones, you'll notice that so far in today's lecture, we've talked about a lot of stuff that we have never talked about cryptography today. Never talked about encryption, never talked about max signatures, nothing. So there's no cryptography today. There will be tomorrow, so come back tomorrow, but not today. What does that mean? That means that this man-in-the-middle attacker can do anything and will never notice because they're allowed to change records. So maybe this answer record is being sent across the network, and the man-in-the-middle attacker stops it, changes this IP address to their IP address, and then sends it to you. You're not going to know that it got changed in transit. There was no cryptography. There's no way for you to know that this is the wrong address. So against the man-in-the-middle attacker, how much security does sorry. Okay, let me try that again. Against the man-in-the-middle attacker, how much security does DNS have? The answer is 0. Like no security. You're your host, I think is what the old slides used to say. So if you're using DNS and there's a man-in-the-middle attacker, you're host. There's nothing you can do. You just have to let them attack you. What about on-path attackers? It's a little bit harder, but again, we've seen this before, which is the on-path attacker can't just change records, but they can poison the cache by sending a spoofed response. They can pretend that this is a message from the name server and then give you a malicious answer. And the condition for them to succeed is, as we've seen, they have to get there first, right? Again, the resolver is expecting one answer, so whoever gets there first will be accepted. And if the attacker gets there first, their answer will be accepted. So it's a race condition. Does the attacker have to know any values? Well, no, because they can see the original DNS request. So what they can do as an on-path attacker is read this request or this response, change whatever they want to add a fake answer, and then fire off their packet and make sure it gets there first. So there's nothing for them to guess because they can read everything and create their own response. So this is basically exactly like TCP so far, right? Against the man in the middle, no security whatsoever. Against an on-path attacker, no security whatsoever because the attacker can race and they don't have anything to guess. So they can always win as long as the packet gets there first. What about off-path? Now it gets a little bit harder. And again, the idea is just like TCP. So in TCP, we had to guess the sequence numbers as an off-path attacker. In DNS, you have to guess the ID number because you don't know the ID number if you can't read packets. And if someone makes a request with ID number 20, and you as an off-path attacker spoof a response with ID number 50, the recipient's going to be like, wait a minute, this is not what I asked for. I made a request of 20 and you're giving me 50, that doesn't make sense. So it's not going to accept it unless it has the right ID number. So the off-path attacker has to guess this value correctly. And if they don't, their request or response will be rejected. So how hard is it to guess? Well, if we're being good, and this is why we said ID numbers have to be random, if you have correctly generated random ID numbers, then the odds of guessing are 1 in 2 to the 16, which I think is 65,536. So not great odds, right? You have to try around 65,000 times before you succeed. And that could take a while, right? You're waiting for this person to send 65,000 requests. You're going to be here a while. Okay, so that's good if the ID number is randomly generated. Sorry. And this is kind of small though, right? If you think back to crypto lectures or, I think mainly crypto lectures or even web lectures, the kind of numbers we were seeing for avoiding brute force were what? They were like billions, right? Like 2 to the 32 is in the billions, right? Or the canary or whatever, memory safety. We were thinking of numbers in the billions or trillions, or 2 to the 128, which is like a quintillion, whatever, right? We were thinking of astronomical numbers. This one is 65,000. It's a lot smaller than what we've seen before. And this is actually not big enough for one reason, which is the attack we're about to see next. So maybe if we had to wait for the victim to make 65,000 requests, then yes, this might be okay, because it would take a very long time for anyone to make 65,000 requests. But what if we're not waiting for the victim to make 65,000 requests? What if we take matters into our own hands and we force them to make a ton of requests really quickly? What would happen then? And that's what brings us to the Kaminsky attack. Almost, I forgot this one more slide. This is all assuming the ID number is randomly generated. What if you're being less creative and less security minded and you just increment the ID field? You can do this. So you can, sorry, I don't know if there's a diagram here, but let's just walk through it. So if you're off path, you can do this. You can trick the victim into visiting your website. We saw how to do this in the web lectures already. So the victim visits your website. That means they're going to make I guess this is a way to trick them. They're going to make a DNS query for your website, attacker.com. If you control the attacker.com name server, guess what? You are going to receive a request. If you receive a request, what have you learned? You just learned the ID field because you see the request that was sent to you. What do you do now? Now you can make a request for google.com. The victim will make this request if you trick them to do that. The attacker knows the ID is one more than the previous one, so now they can spoof the response and guess the ID field. So if you're not secure and you just increment the ID field by 1, you're giving the attacker a very good opportunity to guess. All they have to do is trick the victim into making a request to the attacker first. The attacker learns the ID field, then trick the victim into making another request, and now the attacker can spoof because they know the ID field. So that's an example of an attack that you can do if the ID field is not random. So you have to be very careful that the client or the resolver is generating random ID fields. Okay. And it's so important that it's in bold here. So yes, make them random. Okay, so sorry about this. Back here we said 65,000 is too small. Now we're going to see why it's too small, which is what if the attacker tricks the victim into making lots of requests really quickly? That's called the Kaminsky attack. So we're going to again use this strategy from before. If we use some method like the image tag to trick the victim into making a request, the browser is going to make a DNS query. And if the query succeeds, right, let's say the legitimate answer got there first, or the off-path attacker guessed wrong. So something has gone wrong, and the legitimate answer has won. What happens? The browser will cache the legitimate record, right? That's what the cache is for. So what does that mean? That means the attacker is locked out. The attacker can't even try again until the record has expired. And the records, as we saw, can be cached for 24 hours, 7 days, a while. So if we're using kind of a normal attack structure, then you get one race or one guess. And if you're wrong, you're locked out for a week. You have to stop trying because the browser is never going to make the query again. They will just look at their cache. So that's not good. But one really tricky thing to note here is something that Dan Kaminsky noted. I think this happened like 20 years ago. But Dan Kaminsky, who used to research in security before he passed away, said, well, what if DNS clients do cache additional records in the additional section. So what if we sneak the answer into the additional section instead of putting it in the answer? That's kind of clever. And what does this look like as an attack? So we're going to combine all those things that we just thought about into this very clever, a little bit hard to wrap your head around, but quite clever if you see it, attack. So instead of trying once and then being trapped by the cache if you fail, we're going to find a way to let the attacker try over and over and over again until success. So here's what the attacker is going to make the victim visit. You, as the victim, visit fake1.google.com, fake2, fake3, fake4, and you start to see a pattern. All of these are completely fake domains. They don't exist. What does that mean? That means every single time the client makes a request to the domain name, what do they get back? Nothing useful, right? The legitimate answers will just say, this doesn't exist. You get nothing to cache. Maybe you get to cache that this is not an existing domain, but again, nothing useful has been cached. So if you have been querying legitimate websites and you failed and the legitimate person won, then google.com gets cached. If the attacker is making the victim visit all these fake websites and the attacker loses a race or guesses the wrong ID, the worst that happened is some fake non-existent thing got cached. Not the end of the world. I can keep trying because the attacker or the victim is still going to make requests for fake 2, 3, 4, 5, 6, and so on. What is the attacker going to put in their spoof response? So how are they going to try to win? They're going to add this in the authority section, but crucially, they're going to add this in the additional section. They're going to add google.com has this IP address 6666. Why is it okay that this is in the additional section? Does it pass bailiwick from before? It does, because who are we asking for this request? We're asking google.com to tell us the IP address of fake4.google.com. So if the attacker puts this in the additional section, it will pass bailiwick because google.com can certainly answer a record for www.google.com. So if the attacker wins, or when the attacker has tried enough times that they win, the attacker will cache the record for google.com or force the victim to cache the record for google.com, and now the cache is poisoned. So this is a very subtle, very clever attack. It took a long time before anyone noticed it, but it can happen. And the way you do it is you force the victim to make lots of fake queries. If the attacker loses, nothing useful got cached, so they can keep trying and keep making these fake queries. And eventually one of them will succeed and the cache will be poisoned. Any questions on this one? Because this is definitely a tricky attack. Okay, we're almost done. Last slide, so hang tight. How do we defend against this? This is really tricky. And as we said, if the attacker only has to try 65,000 times, they can definitely force your computer to make a couple of thousand requests. That is very doable. So how do we stop that? We need more randomness. This is the record structure. It can't change. Where do I add more randomness? Well, if I look carefully, there's one place where we said the number can be anything. So if the number can be anything, let's randomize that too. Now, not only does the attacker have to guess the ID number, but they also have to guess what random source port did the client choose. Remember, this source port is like the room number in the apartment. It can be whatever you want. So modern DNS resolvers will always pick something random here so that the attacker, off-path attacker anyway, not only has to guess this 16-bit value, but also this 16-bit value. That's a total of 2 to the 32 values. I don't know why this is 48. I think it should say 32. Wait. No, it should say, let me think. I think it should say 32 because is the source port 32 bits? I don't know. I have to go back and look. But basically, you add more randomness. So now the attacker has to guess a lot more things, and the Kaminsky attack gets a lot harder. Instead of trying a couple thousand times, to succeed, you would have to try a couple billion times, which is probably not happening. So source port randomization is about the best you can do against Kaminsky. So the Kaminsky attack will still happen, but it's going to be so hard and take 2 billion tries That is probably not going to happen today. There are other ways to increase the entropy. You can add some random capitalization in the domain because capitalization doesn't matter, or some other clever ideas like that. Okay, so that's the defense. It's just to add more randomization. Another defense is just don't cache glue records. So if something shows up in the authority section, instead of just automatically caching it, you should make a separate request and double check that it's the correct record before you cache it, or just don't cache it at all. So you do need to use the glue records, but just don't cache them. And that can also solve Kaminsky, because Kaminsky is always poisoning in the additional section. So if you never cache additional section records, or if you always double check them, then you're a lot safer against Kaminsky. So that's another defense. Problem is, I don't think most DNS resolvers implement this. So source port randomization is definitely the modern way to go. But this can also help. Yes. Okay. And there are some different implementations. Some do, some don't. Okay. And yes, there's some politics in TNS. Can you believe TNS is politics? It does. Okay. Here's a slide on if you want to profit from DNS attacks and make some money and be an attacker, you can do this. I do not recommend being an attacker because that's very illegal and bad. So let's skip this. And now we're at the summary with 1 minute to go. So what did we talk about today? Today was all about DNS, the protocol for translating human readable domain names to IP addresses. The way to do this is have a bunch of name servers on the internet. Their only goal is to answer DNS queries for you. We arrange them in this tree. And the idea is if you want to make a lookup, you start at the root and you work your way down the tree until you find the answer that you're looking for. So you make a request here, they say, I don't know, go ask this person. You make a request here, they say, I don't know, but I can tell you to ask this person. And then this person finally gives you the answer. So you work down the tree. And remember, there's a stub resolver that asks the recursive resolver to make the lookup. So everyone in a local network asks the recursive resolver to do the work for them, and the recursive resolver gives them the final answer. And that means the recursive resolver is pooling the cache for everyone else. We talked about what the message structure is like. So we use UDP to be fast. We have an ID field for matching requested responses. This should be random for security reasons. And we encode data in records. So there's an A record for mapping domain names. There's an NS record for designating that this server can handle this zone of domains. There are 4 sections. There's a question section, answer section. There's an authority section and an additional section to tell us where to go next if the name server didn't know the answer. And resolvers tend to cache as many records as possible until their time to live expires. And finally, we talked about security. So there's a cache poisoning attack where you send a malicious record that gets cached, and now this bad record is staying in their cache. And this causes packets to be sent to the wrong place. For example, the attacker could receive the packets that are meant for Google or some legitimate server. There are a couple of risks that we talked about. Malicious name servers could be around. So how do we stop them? We use bailiwick checking. We only accept records if they're in the right zone. So Berkeley is not going to send a record for MIT. So if, as a resolver, you get a record from Berkeley that claims to have a record for MIT, don't accept it. Then we talked about network attackers. If you're a man-in-the-middle attacker, DNS is not secure. If there's an on-path attacker, DNS is not secure. They can race. If there's an off-path attacker, DNS is kind of secure. They have to guess the ID field. That means you have to make the ID field random. But they can have a very good chance of guessing by using Kaminsky. So they can query non-existent domains and put the poison record in the additional section, which can be cached. And this means the off-path attacker can actually try over and over and over again, thousands of times until they win. The way to defend against that is to use source port randomization, which adds more bits to guess. And that makes Kaminsky almost impossible today. So this is about as good as we can get with regular DNS. Tomorrow, we're going to see how you can add cryptography to make DNS a lot better, because this existing method of DNS is not that good. So tomorrow, we'll see how to make it better. Any final questions before we sign off 2 minutes late? Okay, if not, we'll see you all tomorrow. I don't want to keep anyone too long.